In 1905, Albert Einstein made a great discovery. What could that be? What's going on, guys? It's Richard Zhang, and I got a special guest right beside me, Jonathan Eaton. Thanks for coming on the show today. How you doing?
I'm doing good, man. Thanks for having me on. Haven't seen you in a while.
Of course, good to see you too, but I actually invited you on the show to talk about Einstein's theory of relativity.
For sure, let's get to it. So the first thing we need to acknowledge is that to understand time dilation and his theory of relativity is that objects move relative to each other. So there's no absolute motion and there's no absolute rest. For example, if you're in a stationary car in front of a clock, the clock would tick at the same pace as we know it, but if we're able to move at the speed of light away from that clock, the hands on the clock would appear to basically stand still.
So if we wanted to make that happen, how fast would we need to travel?
Well, the speed of light is 186,000 miles a second, and we need to be essentially moving that fast or faster, which is just not possible. As Einstein concluded, this is because the faster you move through space, the slower time becomes. Also, the speed of light is always the same. It is a constant.
So the speed of light is a constant, but how people observe it can be relative?
Yep. For example, let's create a scenario. I'm going to need you to imagine you and I are each theoretically sitting inside two sets of two mirrors, facing each other with a light beam bouncing between them. But your set of mirrors is moving and mine is stationary.
So just to be clear, I'm sitting between two mirrors facing each other, and I'm moving, and you are also sitting between two mirrors, but you are not moving, and there is a light beam bouncing between each of the mirrors. Am I getting that right?
Yes, exactly. Now, we know the speed of light will be the same, and that the light beams will hit the bottom mirror after the same amount of time has passed for each, but since your light beam will actually be moving a further distance than my light beam, how would that be possible?
I'm not sure. Is that because time slowed?
It is, actually. This happens because time has slowed down for you relative to me. To put this much more simply, we know that speed equals distance over time, and because the speed of light remains the same but the distance increases, that means the time must also increase with it. Now, of course, this theory of special relativity is only true for when the speed of the objects is constant, as we talked about. However, Einstein realized that in the real world, things speed up and we experience the effect of gravity. To account for this, Einstein developed the theory of general relativity.
And I shortly read about general relativity. Is this where space-time comes into play?
It is, actually.
And for listeners out there, space-time is the concept that time and three-dimensional space is interwoven into a four-dimensional universe.
Exactly. But another crucial idea involved is the equivalence principle, in which the equivalence of the gravitational force and the force experienced in accelerated frames of reference. This, combined with the idea of space-time, can summarize Einstein's general theory of relativity. Let me explain. If you were to be in an elevator and you dropped a ball and it fell to the floor, you would assume that you were on Earth and the gravity pulled the ball to the floor. However, you could also be traveling through space at a constant acceleration, causing the appearance of gravity.
Okay, I got it. The theory of relativity isn't too bad after all.
Now, general relativity is truly defined by loads of extremely complicated math equations, which is essentially unfathomable by people outside of the 1% of people, the Einstein type of people. That being said, we can go over a great conceptual representation of it.
Right. Now, isn't it true prior to this discovery, we used to think of the universe as a basic, rigid, geometric universe?
It is. But we learned that just as a shape drawn on a piece of paper can be distorted by bending the paper, space-time is distorted. Space-time is distorted and bent by massive objects like planets. Resulting from this distortion of space-time between massive objects is what we observe as gravity.
That's quite a hard visualization.
It absolutely is. And it is actually physically impossible for our brains to visualize, so we use analogies like the piece of paper to help comprehend.
Now, when doing my research before having you on, I read a quote by one of Einstein's later colleagues, John Wheeler, and it read, "Space-time tells matter how to move. Matter tells space-time how to curve."
That's exactly right. And it's quite a hard concept to grasp because it goes against exactly what we commonly know. But yes.
Right. So, if you don't mind, can you just try to summarize this complex results of this theory as it applies to us?
I can. The results of Einstein's general theory of relativity is that gravity is actually the result of bent spacetime. It also predicted the existence of black holes years before they were discovered. It also allows for the theoretical possibility of time travel.
Time travel. Is this because if we were theoretically able to move faster than the speed of light, we would be able to go back in time?
Yep, that's exactly right.
Okay, wow. Well, you heard it here first, everyone. Time travel is possible. But anyways, that's all the time we got today. Thanks for coming on, John.
Thank you, man. Thanks for having me.